Okay. So I gave a presentation similar to this about 2 years ago. I decided to give it another shot, mainly because the last presentation was focused on PowerPC, which is what we were using for the consoles back then, and now we're all on Intel or AMD x64 platforms. So there's some things have changed, and I'm going to give it another shot. So why would you want to debug optimized code? The main reason for doing this is that you don't always have the luxury of dealing with nice debug code with all your asserts and all this stuff enabled. In cases like crash dumps, when you're dealing with some other compiled library that you don't have source to, or simply the worst case is when you have bugs that only occur in like release or ship executables. The sad truth is that I also find it a lot of fun. So the problems that you are presented with when you're dealing with optimized code is that local variables in your functions are no longer reliable. They may or may not exist as far as the debugger is concerned. In the best case, the debugger just won't show them. In the worst case, the debugger will show them with incorrect values. And secondly, stepping's unreliable. It doesn't follow the source code as it should. It will jump around wildly throughout the place. So why does this happen? Here's my little piece of example code that I'm going to use throughout this thing. It takes in 3 integers, multiplies the first 2 together, adds the third one onto it, and returns the result. It's exciting stuff. Here is the debug executable. This is on Windows 64-bit. So here's this piece of code with the C source code and the disassembly mixed in. I'm not going to ask everyone to follow this. I can't even follow all this, but just to prove that here's the function and here's all the code that goes along with it. What's happening in this? We have 5 lines of C code that compiles into 23 assembly instructions. Each statement compiles into a block of instructions, and that block reads in all this data from memory, operates on that data, and writes that data back out to memory again. So each block is like a self-contained piece of code. And the debugger, because of that, the debugger knows where all your variables are at any point in time. If we take a look at this piece of code right here, which is taking C and adding it on, these 2 statements right here are reading in values from memory into registers. This add opcode here is actually doing the work right here of adding on. And then these 2 right here store that value back out into memory. RSP right here, the address of the stack pointer is actually where the result variable is. So the debugger knows all this. It knows where these values are coming from. It knows where they're going to. So it can easily display in the watch window or in the locals window or the autos window what those values are. The optimized version is much, much shorter. You just have 3 operations. There's 0 writes at the memory. There's no, this redundant operation right here is removed. There's only like 3 instructions in the whole thing. So what's happening here? We have 5 lines of code compiling down to 3 instructions. There's no longer any kind of direct mapping between the lines of C code and blocks of assembly instructions. The pointless or redundant statements have been removed by the optimizer. And everything is done in registers. Nothing is written out to memory. The local variable in the previous instruction just doesn't even exist in this version of the function. Something else that happens in this is that the input state, the actual arguments that come in, get overwritten during the progress of the function. So what can we do to work with this code? You don't need to be an assembly language guru. We aren't writing it, we're just interpreting. So our goals are to get our bearings in the code, try to find out where we are, understand how and where the data is moving and how it's stored, and determine where and when we can get access to the data you're interested in. The when is kind of important because when you're dealing with unoptimized code, it doesn't matter at what point in the function you're at, the data is always going to be there in memory where it's meant to be. While with an optimized version of a function, it might just exist for a short period of time in memory, it may just exist in a register, and you need to be able to find out at what point in the function you can actually get the data that you're interested in. So what we're going to do is we're going to work out how we can determine what A, B, C, and the result values are in the example code. So the tools we need, we're only going to use the disassembly and the watch window in this, but the tools we need in general that you may or may not be familiar with is the disassembly window. The disassembly window is just a source code window where you right click and you can do go to disassembly. There's a few options you want to enable, like ensure the addresses, and it shows the source code and symbol names, which will kind of track things out a little bit. The registers window, which you have very little use for outside of this purpose. It'll show you what the value of all the different registers are in the CPU. And then the watch window and the memory window. So registers. Registers on Intel x64, we have 16 64-bit registers. These are all them up here. They have slightly kind of different names, which means they're kind of referenced in different ways. So if they have OR at the start, they're 64-bit. If they have E, or in the case of these numbered registers of D at the end, they're 32 bits. There's 16-bit and 8 bits, but you'll rarely encounter those. These ones all here are like legacy x86 opcodes, or registers, sorry, and then when they expanded to 64-bit, they added in these additional numbered ones. It would have been a lot easier if they just used the numbered ones. Also, we have 16 SSE, AVX, or SIMD registers. These are, on x64, these are used for floating point. It doesn't use the x87 floating point CPU or its register stack anymore. Both of these are actually the same register, they're just different ways of referring to it. When you refer to it as XNM0, you get the 128-bit version. YNM0 is the 256-bit version. And like I said, they're used for all the floats and doubles. So registers aren't magical in any way. You can just think of them as unsigned 64-bit integers if they were C variables, but they aren't typed. All they do is just store 64 bits of data. So at any point in time, a register could be storing a memory address, any kind of integer type between 1 and 64 bits, a class or a structure if it's small enough to fit into that register, or really any 8 bytes of data. But the most important thing is you can put them into the watch window and just look at what their contents is, as if they were any kind of local variable. So you can just put the name in, you can put in ECX or RCX, whatever, and it'll just show you what that value is. If you happen to have a symbol called ECX, you can prepend it with the $sign. You can use them in expressions, and then if you have determined that EDX stores a pointer to an entity T, you can just in the watch window type in an expression like this, and it will happily display you whatever that it thinks EDX is pointing to. So when you're actually looking at disassembly, you don't necessarily need to know what each opcode does. The most important thing to know is that in the Intel syntax that we see in Visual Studio, the data moves from right to left. So in this case, the value that's in ORCX gets moved into ORAX, which is what the move instruction does. And here's what the C equivalent would be. These square brackets right here are like a pointer dereference. So what's happening here is the value that's stored at the address that ORDX is pointing to is added onto ORAX. And here, the address that ORAX is pointing to is filled with the value that's in ORDI. You're going to see a lot of opcodes that you don't understand. I see opcodes I don't understand all the time. And sometimes there's some decoration in front of these specifying the size of the address you're writing to. Sometimes there isn't. But it's really, the most important thing is just to know that when you're looking at an opcode, the instruction or the data on the right is going to end up in the register on the left, or the memory address on the left. So function calls. The ABI, the application binary interface, defines the calling conventions, and these are very strictly enforced. So every function you call has to follow a set of rules as to how variables are passed in and how data gets sent back. And this is obeyed everywhere, regardless of whether you're dealing with optimized or unoptimized code, whether you're calling into a library or whatever. It all has to follow these same set of rules. Windows 64 and Durango share the same ABI for the most part, at least as far as this is concerned. It's a big improvement over the 4 or 5 calling conventions they had on 32-bit. It's still a little bit limited, but the most important thing is that values can now be passed in registers. So the first 4 integer or pointers or objects that are less than 8 bytes that get passed in can be passed in through these 4 registers, and they'll always be passed in for those 4 registers. And if there's floats and doubles, it'll be passed through XMM0 to XMM3. Everything else gets put on the stack, and the return value is always going to be in either RAX or XMM0, depending on whether it's an integer or a float. If it's an object that's being returned, it'll be a pointer in RAX. So this function right here, which is taking a int, a float, an int pointer, and a other float, the first int will go into RCX. The second float will go into XMM, this should actually be 1, now I realize this. The third, the integer argument will go into R8, and the final float will go into XMM3. I kind of messed up the one really important thing here, which is that, so it's not like the first 4 integer arguments that you encounter will end up getting put into here, and the next 4 floats will get put into here. It's like only the first 4 arguments are candidates for going into registers. So if you have a function that takes 3 ints and then a float, it'll be int, 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 and then the float will go into XMM3. And if you had a function that took, say, 3 floats and an int, it would be XM1, 2, 3, or 1, 0, 1, 2, and into R9 would be the final argument. This is different from Orbis, which has a much nicer and more flexible ABI. It's based on the System 5 AMD 64 ABI. You have 6 registers available for integer pointers, and you have all 8 SSE2 registers available for float pointers, and the return values are the same in RAX and XM0. In this case, it will, if you have a function that takes, like, any of the integer arguments in a function will end up into these registers, any of the floats will end up into these. It doesn't matter what order they come into, it fills it like a, almost like an alligator. So here, the first argument gets into RDI, the second one into XM0 because the float, third one into RSI, XM1. There's actually a lot more complexity here. If you passed in like a 16-byte structure into this function, it would get put into RDI and RSI, copied into those registers separately as 8-byte blocks. And it can merge up to, like I believe, a 64-byte structure would get passed in through 4 registers. So that's not everything you need to know, but it's enough to get us the information we want to do for this little example. So let's go back to our example function. Here is the optimized version again. So here, the first integer argument, which is the A parameter here, it's going to be an ECX. We know that from the ABI. The second argument is going to be, which is B, is going to be an EDX. And this operation here is multiplying them together. So, and we know we move from right to left. So EDX is multiplied by ECX, and the result is stored into ECX. The third argument, C, is going to end up in R8, again, according to the ABI. And this opcode right here is going to ECX, which is right now storing A multiplied by B. We're going to take ECX and add R8, which is C, onto it, and we're going to store it into EAX, which is, we know from the ABI again, is where the return value is going to end up. And that's it. So further reading, as far as this is concerned, the 2 calling conventions are very important. We have the MSDN. If you look on their site for x64 software conventions, you'll find a big link to their ABI. I've checked in the Orbis ABI into Perforce because it's kind of difficult to find online. And 2 things I used while writing this were just the guide to x86 assembly and the art of assembly.
One thing, go to the previous slide. Next to last.
This one?
Yeah. Previous in the presentation, you said that the brackets were for referencing a pointer.
Yes. So in this case, this instruction right here is kind of a special case. LEA load effective address. Is that what it is?
Yeah.
It's what it's doing right here. These are in square brackets, but it's not really doing a pointer dereference. It's a shortcut the optimizer is using, because this instruction basically just calculates an address and stores it in a register, EAX. So it can do this addition without having to actually use the ALU. So it's more efficient than actually doing an add instruction. So it looks like it's doing a dereference right here, but it's not really. It's just taking the two values in OR8 and ORCX and adding them and storing them into EAX without using a addition opcode or occupying the ALU. Anything else?
It was just confusing.
Anyone got any questions? I know I flew through that really quickly. So.
Are you going to send us the PowerPoint?
No.
Oh. How do you deal with out of order execution?
Like how the actual processor will deal with
That's
it?
going to make it a lot harder to look at the code.
Yeah, but you won't know what it does. It does it itself.
Yeah, so
Those
actually,
registers are irrelevant. It has its own stack
Yeah.
underneath, so it just decides to reorder stuff for you. Because
So
all that code's mainly interpreted.
so while it says here that like it has 16 registers, I think it actually has 128
It loads and it
registers.
just then goes and assigns what it wants.
Yeah, so these are just what's visible to you. Behind the scenes, the CPU is assigning its own internal hardware registers to these logical registers. So it can just reuse them as it sees whether code actually needs to reference registers or not.
Because most of the instructions are just microcoded stuff. It's decoded into something else.
Yeah.
Plus also the one thing is the instructions are variable length. So if you would move your pointer along by 1 or 2, then the program count of your code will change. It's not like the PowerPC where each instruction is fixed size.
Yeah, the PowerPC was definitely a RISC architecture. Well, this is probably one of the most complex of the complex instruction set architectures.
So how did I and RCX got loaded with anything on that?
So the function that calls that function, it knows, because of the ABI, how it has to pass arguments in. So it will, before it actually does the call opcode, it will set ORCX and ORDX and OR8 to the values it wants to pass in.
So one had C.
Hmm?
One had C, the value of C.
Yes.
And the other one?
ORCX had the value of A, ORDX had the value of B, and OR8 had the value of C.
I thought EAX had the value of A.
No, it's ORCX, ORDX, and OR8. I think they did it that way because on the previous calling convention, if you called a C++ method, this pointer would end up in ORCX because it was the first argument, so they maintained that. So the first argument is ORCX, the next argument is ORDX. Yeah, so RCX is A, ORDX is B. And they get multiplied together and they get stored into ORCX again. So now A has been clobbered by this instruction.
You mentioned that beyond 4 arguments, or in the case of the Orbis, more arguments, that they start passing via the stack. Is there a good way to get a hold of the memory in that kind of situation?
There is. It's a little more complex, and I usually have to kind of guess when I do it because I can never remember exactly what the methods are. But the RSP register is the stack pointer, so you should be able to put that in. You can put that in the watch window if you wish, but you would have to look at the assembly code and kind of see where it's. The easiest way I found is just to see where it's pulling those values off the stack. Usually it'll be like an RSP plus or minus some offset.
There's probably a better chance, though, that you'll be able to see the value in that case.
If it's actually
on the stack.
Yeah, if it's actually passed in on the stack, but there's still no guarantee that you're seeing the correct value, because the compiler is free to reuse that data once the argument has been passed in, or it may just pull it off the stack and never write it out again.
Well, have you seen in practice if that is more or less likely with these?
Have an extra look.
I've seen in practice if you locally assign stuff, often it'll go onto the stack so you can read things more often. Like if you have a problem, recompile your release code and redeclare things so that you have like a copy of it.
Yeah, like there's definitely methods you can use that don't involve this kind of stuff. Like if you just have a global variable you want to save to at a particular point in time, you can look at the state of that. So there's ways you can get at the state as long as you can
It's actually the only good use for volatile as well.
Yeah. Yeah, because if it's a static, or if it's not a volatile, the compiler may just decide not to do the write for you. So it's fine.
Is there a concept of copy and color save registers?
Yes, none of the, so the function you call, the callee, it doesn't save any of the XMM registers, but it does save, I think like, I have to look at the ABI again, but I believe it's like on Orbis, it's like R12 onwards, I believe, is saved.
I see. I guess all the argument registers are probably easy.
Yes, yeah, you have the caller, no, the argument register is the caller.
Yeah, right.
And it can be, that's useful information to know too, because you can look at the, if you know what registers are saved,
Yeah.
you can, if you break out like the call function or the call opcode and you step down to the next thing, then you'll know that certain registers are being restored to their correct values while other registers will have just been destroyed in the process of applying that function.
It's interesting to see that a lot of times a lot of stuff is put on the stack. It seems inefficient to read and write on the stack, but behind the scenes when the compiler actually uses that as registers. So the stack pointer that you see is actually pointing to a lot of registers. So optimizing code for reading and writing from the stack is often useless.
So on the side where you're describing the registers that the Orbis takes in for parameterless, you say the Orbis is better. Are you just completely ignoring the Connect 2 and Xbox's stronger lineup of games? Sony fanboy.
The cloud connectivity actually gives it more registers on Durango.
If it was possible to defend Xbox.
Sorry.
Is
Okay.
there any guide, like, with these facts about how the parameters are passed through the registers, any guidance to how to kind of like make our functions, you know, how many parameters should we kind of like shorten them?
You'll, you know, if you've got 4 or less arguments, you're pretty much guaranteed they'll be passed through on registers. But even if they're not passed on registers, they're still they're gonna go through the stack, which will
We'll probably end
be
up
in the
on
cache
registers
anyways.
anyway. Because it interprets everything, so it will probably see, oh, I can stick this on, and then it makes half the stack registers. So trying to sort of hard go in there and like, oh, if I change this around and try and make the assembly good, you probably make the code slower.
I would imagine that if that was your primary consideration, that I would rewrite the routine to not call that function 8 million times a frame.
Well, there are something that I can go into on Durango is that if you're passing like a float 4 like SIMD value, it doesn't get passed through on registers. It actually gets allocated by the caller, and a pointer to that value gets passed through.
That's why they're all force and line.
Yeah. So 2003, Visual Studio 2003 has a new fast BEC or BEC call, I can't remember what it is called in convention, that passes them on the registers. Orbis right now will pass in float 4s just through XMM 0 through 7.
How does the fast calling work?
This is, so what we're seeing here for Durango is fast call on the registers. The older calling convention I think used to always pass everything on the stack.
mentioned it, I think, you explicitly mentioned it.
I think you have to like explicitly request fast
Right.
call as a method before.
Fast call is from 32 bits.
Yeah, but now this is the only, they've reduced it down from like 5 different calling conventions to just this.
Just this
one.
one. We don't have to do it.
Yeah.
So if you call a class function, a class member function, is there a convention for where this would be?
It will just treat it as the first argument. So on Orbis it'll be EDX, and on Durango it'll be ECX or CX.
So was there no prologue or epilogue code emitted by the monitor?
For this one, no, because it does nothing on the stack. It doesn't reference anything, so it's just literally what it is. I have to turn off whole program optimizations to actually get it to generate this code first.
Well, awesome.
Thank you.
Thank you.